All right, the next work problems we're going to look at are coming from springs. We're going to use a physics law called Hooke's law to do these spring problems. So the next example, we're going to use Hooke's law that states that the force required to maintain a spring stretched 8 units beyond its natural length is proportional to x. So our Hooke's law here is stated here. This is our force. K here is something called a constant, usually called spring constant. So Hooke's law works provided that that constant's not too large. So what we're looking at here is if we had a spring on a frictionless surface here, this is at its natural position, which would be 0. If we now stretch this out to this new location, x, then the force would be whatever the spring constant is for this particular spring times that distance. That's the force needed to maintain that stretched position. All right, so let's try out an example here with a spring. So it says, suppose 5 joules of work is needed to stretch a spring from its natural length of 1 meter to a length of 2 meters. How much work is needed to stretch the spring from 3 to 5 meters? All right, so we got a lot of information here. Let's start with that opening one because it said, suppose 5 joules is needed to, or 5 joules of work is needed to stretch the spring from 1 to 2 here. So from that information, what we can take out of that is we already know an amount of work done. So on here, when we're setting up our integrals, our work is going to be from like kind of the start, and we got to be kind of specific here. This is from the start from the natural length, or it's like position from the natural length. So it's always you're always doing your start from natural, and then your ending amount from natural length. And then we always integrate our force here. In this case, your force is going to be the spring constant. So our spring constant on this one should be our spring constant times x dx. So this is our force right here when you use a spring. So here we already are told the amount of work, so that can go here. In our next part here, what is the limits on this one? Well, this said 5 joules is needed to stretch from natural length, so that would be at 0. So natural length, even though it's 1 meter, that's the natural length is considered 0 to a length of 1 meter. So what we got to figure out is how far did that actually get stretched then? So if the natural length is 1 meter and it's stretched to 2, that means we've stretched it 1 meter. So this would be from natural length of 0 to 1 because that's how far it got stretched is 1 meter there. All right, so next, what do we know about this spring here? Well, we know we got some spring constant x dx. So we're not sure of that spring constant right now. So let's integrate. We got to remember k here is a constant. So if we wanted, we could pull that outside of this. And now we're just integrating x. So that integral, or antiderivative would be 1/2 x squared from 1 to 0. If we put that in place of here, we get, I'm going to write this as k over 2, our constant here. 1 squared is 1, 0 squared is 0, which is just going to be 1. So we end up here that we got k over 2 being equal to 5. If we times by 2 here, it looks like our spring constant in this problem is 10. Now, that's not our answer, but we are going to use that now to answer the next part, because there's a second part to this question. So the second part starts here. How much work is needed to stretch the spring from 3 meters to 5 meters? So now let's set up this second work integral. Okay, so let's start with our limits. 3 meters to 5 meters. Remember, our natural length of this is 1. So we need our starting amount to be how far from the natural length. So here, our natural length is going to be 3 minus 1, or that it's already at 2 meters from its natural length when it's stretched to 3 meters. Our ending amount would be 5 minus 1, again, because our natural length of the spring is 1 meter. And so our ending amount there would be 4. Our work function is kx dx because it's a spring, so we always use spring constant times x. We know our spring constant for the same spring, though, now is 10. So this turns into 10x dx. Now, if we integrate that, that should give us our answer here. Antiderivative of 10x would be 5x squared, 42. Now, to find the amount of work, plug in 4 and plug in 2 and see what you get. 4 squared is 16. 2 squared is 4. So we got 5 times basically 12 here, which would be the amount of work would be 60 joules needed to the amount of work needed to stretch that spring from 3 to 5 meters. Okay, so the big thing when you're doing these, you got to be careful with your limits here. Don't just put in 3 to 5 if the natural length of that is 1. It's got to be the starting length from the natural and the ending length from the natural state. So if that is already a length, you need to subtract to find those new ones. Let's try another one here. Next example says a force of 40 newtons is required to hold a spring that has been stretched from a natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 to 18? Okay, so one thing that is going to come up in this problem that we have not seen so far is that our measurements are not necessarily in the units that we want them to. If we're working in newtons, we know that we want this our length measurement to be in meters. So we got to convert these measurements over to start with. So 10 centimeters, if we want to go centimeters to meters, remember there's 100 centimeters in a meter, so we need to divide these all by 100. So 10 centimeters is going to be the same as 0.1 here. So this would be 0.1. 15 divided by 100, that's going to be 0.15 meters now. I suppose I should label meters. This is also 0.15 meters. And this would be 0.18 meters. Okay, so make sure that you're using the meters in this one. All right, so next, it says 40 newtons is required to hold a spring that has been stretched from its natural length of 10 to a length of 15. So what we want to do here is now solve again for that K value, kind of like the last problem here. So let's set up our integral here. So the amount of work done. Oh, sorry, this is a force. Sorry. So if it's a force of 40 newtons, we could go right to our equation here because we know this is a force. So force in this case is equal to our spring constant times the distance. We got our force here of 40. we're trying to find our spring constant here, K. So how far has that spring been stretched here from natural length to this? Looks like it got stretched there. If we subtract those, 0.1 minus, sorry, 0.15 minus 0.1, that spring has gotten stretched 0.05 meters or 5 centimeters basically. So now if we divide, we can get our spring constant. So if we divide 40 divided by 0.05, that's going to give us a spring constant here of 800. So there's our spring constant. Now we can use that to answer the second part of the problem. So our work done in stretching the spring from here to here now, we got to find, again, our starting amount from the natural and our ending amount from natural here. And then we got our kx dx here. So the amount of work, what's our starting one? Well, 15 is our starting. That is not the natural length. Natural length is 10 centimeters. If we subtract that, that's 5 centimeters away. So our starting amount is 5 centimeters away, or that's 0.05 meters. Our ending amount's 18 from the start. That's 10, so there's a difference there of 8 centimeters. So change this from 8 centimeters to meters. That'd be 0.08. We know our K value is 800 x dx. So if we integrate that, that should give us the amount of work being done on this one. Now to integrate this one, we just gotta find our antiderivative and so on that we've done before. So this would be x squared. So we got 400x squared here from 0.08 to 0.05. Probably want to maybe use calculator to do this one, so you got to figure out what's 0.08 squared minus 0.05 squared, times it by 400, and we should get this one. Let's use calculator to figure this one out. So we got 400 times 0.08 squared minus 0.05 squared. Looks like the amount of work is 1.56 joules. Okay, let's have you try one out. See if you can read through this one and see what you get for the work done on the spring here. All right, hopefully you've had some time to attempt this one. So first piece of information we get here is 30 newtons is needed to maintain a spring from natural length of 12 to 15. So if we use our force is equal to our spring constant here, we know our force is 30, spring constant, and then the distance that is needed to get that force is 3 centimeters if you subtract these two. But remember, we need this in meters to make it work with our units here. So that's 0.03 meters. Divide and you get a spring constant of 1,000. So we're going to use that same spring constant over here for the next part, times our distance, and we're going to integrate. And it says how much work is done in stretching the spring from 12 to 20. Well, 12 is our natural length here. So that would be starting at 0, because 12 minus 12 is 0. To move to 20, 20 minus 12 is 8 centimeters. That needs to be our top limit then, and in meters that would be 0.08. So if you integrate that, you should get 3.2 joules. So hopefully you came up with the same amount.